Welcome to Mathematics. Today we'll be solving the Pearson Edexcel IAL January 2024 paper of Physics Unit 5. In question number 1, we are given that ice at 0 degree Celsius melts into water at 0 degree Celsius. We have to choose which row from the table containing the mean molecular kinetic energy and the mean molecular potential energy change is given. Now, since the temperature before and after melting is the same, the molecular kinetic energy will remain the same. So, C and D are not our answers, since the molecular kinetic energy changes the temperature. So, if there is no change in temperature, even if the state changes, there won't be a change in the molecular kinetic energy. Now, for ice to melt to water, its structure, the potential energy of its structure has to increase, since ice has a closely packed structure, while water doesn't. So to cause this change, we need to increase the potential energy. So this and this. So B is our only option. Now in question 2, we are given about the stellar parallax method to determine the distance to stars. We have to choose which of the following statements is correct. In the trigonometric stellar parallax method, we view the angle of a close by star against a backdrop of distant stars. By measuring it against a backdrop of distant stars, we can find this angle and this angle. The angle in between will be alpha plus beta. So using the angle, and we know that the radius of Earth's orbit is 1 astronomical unit. We know that distance. So using that, we can find the distance from Earth to this star over here. So measurements are made against more distant stars is the correct answer. Stellar parallax are usually used only for nearby stars. If the stars are too distant, this angle over here will become smaller and smaller, and at some point the angle will be too small for us to even measure. So this is not it. It's used for nearby stars, not distant. The calculations for this method does not contain luminosity, so luminosity does not need to be constant. And option D, if the stars are distant, the parallax angle will be smaller, not greater. So the parallax effect is greatest for nearby stars, not distant. So this is wrong as well. Now in question 3, we are given that the mass of a muon is 0.113. We have to find its mass energy. So for that, we have to use E equals to mc square. We have to take the mass in kg. 1 U is equal to 1.66 into 10 to the power minus 27 kgs. So this is the mass in kilograms. And then we multiply the speed of light in vacuum squared, or speed of causality. So option C is our answer. The rest do not match. In question 4, we are given that a mass which is oscillating with simple harmonic motion. We have to choose which of the following statements about its acceleration is correct. Option A isn't always true, since when the object is moving from the extreme to the, if this is the center of oscillation. When it's moving towards the center of oscillation, its velocity and acceleration are in the same direction. This is not the answer. The acceleration is also not always in the same direction, because when the object is moving away from the equilibrium position, the acceleration is towards the equilibrium position while the velocity is away from it. Option C is wrong. The definition of simple harmonic motion is that the acceleration is proportional to the negative of the displacement. The minus represents that the acceleration is always towards the equilibrium position. So it's opposite to the displacement. So if this was the displacement from the equilibrium position, the force will always be in the opposite direction, or the acceleration will be always in the opposite direction to that displacement. So it's always towards the equilibrium position. D is our answer to question 4. Now in question 5, we have to choose which of them correctly describes the spontaneous nature of radioactive decay. Spontaneous means that we do not have control over how the decay occurs. We cannot change factors to influence when the decay will occur or how much decay will occur. In option A, it says it's natural process. This does not mean it has to be spontaneous. There are a lot of natural processes that we can affect by changing temperature, pressure, or other variables. We can also affect random processes. So this is also not our answer. Option C states that we cannot influence when the next decay will occur. This is the correct answer. Now option D says we cannot predict. In a lot of cases we can predict the decay rate. We can also plot functions. We know the half-lives of radioactive elements, so we know how much they are gonna decay and how many of them will decay, but we do not have any control over it whatsoever. The part of us not having control makes it spontaneous. Now in question 6, we are given the information that the planet Mercury orbits the Sun in an elliptical orbit. As a result, the speed of Mercury varies as it orbits the Sun. Now we are given the GPE and the speed, that the change in speed and GPE when as Mercury approaches the Sun. So as Mercury gets closer to the Sun, so an orbit like this. So this point is far away from the Sun, while this point is closer. So when it's moving closer, we have to state what changes happens to its gravitational potential energy and speed. As Mercury gets closer to the Sun, its gravitational potential energy will decrease, since its value of del H will change. If we get more technical, we can write that the GPE minus Gm by R1 times M minus GMM R2. This is R2, this is R1. Since R1 is bigger than R2, so the term GMM by R1 is smaller than GMM by R2. So my bad, we'll have final minus initial. This will be over here and this will be over here. R1 is larger than R2. So this value is bigger than this value. So the change in GPE will be negative, which would mean that the GPE decreases. If the GPE decreases, the KE must increase, and if the kinetic energy increases, the speed will increase. So the speed should increase and the GPE should decrease. So option B is our answer. Now on to question 7. We are given that a mass oscillates with simple harmonic motion and that it has an angular velocity of 2 radian per second and a maximum velocity of 10 centimeter per second. We have to find the magnitude of the amplitude in centimeters. We know that Vmax is the angular velocity times the amplitude. So 10 centimeter per second is equals to 2 radian per second times A. So A would be 10 centimeter per second divided by 2 radian per second. We'll get our answer in this form. So A will be 10 by 2 centimeters. Now in question 8, we are told that a mixture of helium gas and hydrogen gas is kept at room temperature. Which of the following would be correct? The first option states that the mean kinetic energy of the helium molecules is greater than the mean kinetic energy. This would be wrong because the mean kinetic energy would be the same because both of them are kept at the same temperature. At same temperature, kinetic energy, mean kinetic energy for any molecule is the same. Option B states that the mean kinetic energy of helium would be less than the mean kinetic energy for hydrogen. This would be wrong as well, they would be the same. Now the next two options are about the mean square velocity. Since we know that the kinetic energy would be the same, we can write the mean kinetic energy as half times m and then the mean square velocity. Now the kinetic energy must be this, the average mean kinetic energy for hydrogen and helium molecules must be the same. However, the mass of helium molecules, if we consider helium, mass of helium molecules will be greater than that of hydrogen molecules. So to balance it out, the mean square speed must be smaller for helium. So if we explore our options, option A says that the mean square speed is greater for helium. This wouldn't be the case. It would be smaller for helium to balance its greater mass. So option D is our answer. Option D states that the mean square velocity for helium molecules is less than the mean square for hydrogen. This is the correct answer. Now for question 9, we are given the intensity wavelength graph for two different stars. We have to use Wien's law over here. For star X, this is the peak wavelength. For star Y, this is the peak wavelength. We know that the peak wavelength multiplied by the temperature is constant, or Wien's constant over here, 2.898 into 10 to the power minus 3 meters Kelvin. For star x, lambda is smaller. For star x, lambda is smaller, so T must be greater. For star y, the peak wavelength is greater, so the temperature must be smaller for it to become be a constant. So temperature of x will be greater than temperature of y. So A and B are out since they say that temperature of y will be greater. Now we have to talk about the frequency. We know that the wavelength times the frequency is equals to the wave speed, which is a constant. So frequency is the speed of causality by wavelength, or frequency is proportional to 1 by lambda. For star x, the wavelength peak wavelength is larger, so frequency is smaller. So x has a lower frequency. So C is our answer. Oh, my bad. X has a lower peak frequency, so its frequency must be greater. The wavelength of star y, the peak wavelength of star y is greater, so its frequency will be smaller. D will be our answer, since x will have a higher frequency than star y. Now for question 10, we are told that the Earth has 10 times the mass of Mars and twice the radius of Mars. We have to find the relationship between the gravitational field strength at Earth and at Mars. Now the gravitational field strength is the gravitational force per unit mass. G is gravitational force per unit mass. So G is equals to Gm by r square divided by m. So G capital M small m by r square divided by small m. G will be equals to Gm by r square. So G is proportional to m by r square, since capital G is a constant. Now we are told that Earth has 10 times the mass of Mars and twice the radius. So radius of Earth is twice the radius of Mars. Mass of Earth is 10 times the mass of Mars. The ratio m by r square for both Earth and Mars should be the same. Sorry. It wouldn't be the same. We can work easier with this. So gravitational field of Earth will have a value of G times 10 times the mass of Mars divided by 2 times the radius of Mars whole squared. So G Earth is equals to 10 by 4 Gmm by Rm squared. If we look at this thing over here, Gmm by G times the mass of Mars divided by the radius of Mars squared. This is the gravitational field strength at Mars. So gravitational field strength at Earth will be 10 by 4 times the gravitational field strength at Mars. So gravitational field strength at Earth is 2.5, the gravitational field strength at Mars. A is our answer. Now moving to section B. In question 11, We are given a Hertzsprung-Russell diagram with some groups that shows some groups of star. P, Q, R and S refer to different areas of the diagram. We have to describe a possible evolutionary path for something in area P. Area P is a massive main sequence star. Area R is around the area where the sun lies, and P is where the heavier main sequence stars are. So stars in area P are large main sequence stars and you have to keep in mind it's still a large main sequence star. It's not a blue giant. This is a large main sequence star, but it's not a blue giant. You can also write this is a main sequence star as its own. Don't have to mention that it's large, but this is not yet the blue supergiants that are over here. So this won't form a neutron star or a black hole. This will just go to the red giant or red supergiant section and then go to the white dwarfs section. So from area P it moves to area S. And from area S they move to area Q, where they are white dwarfs. Now you need to catch the hint that this is not a blue giant at first, because we are given this diagram where there is only one section for red giants. We don't have another section over here for red supergiants. So if we don't have some different place to take it, a region T for example, where the red supergiants are, so we have to take this hint that this is gonna form a red giant. Now for question 12, we have a simple pendulum with a period of 2 seconds on Earth. We have to calculate its period if this was on planet Venus. The mass of Venus is given, the radius of Venus is also given. Now we know that the time period of a simple pendulum is 2 pi root over L by G. Now we don't know the length at first, but we know the time period at Earth and the gravitational field strength of Earth. So the time period 2 seconds will be equal to twice pi the root over of the length divided by 9.81. So root over L by 9.81 is equal to 2 by 2 pi. We can square both sides and get L by 9.81 is equals to 1 by pi squared. L would be equals to 9.81 divided by pi square. Now the gravitational field strength at Venus would be equals to the gravitational constant So capital G, which is 6.67 into 10 to the power minus 11, times its mass, which is 4.87 into 10 to the power 24, divided by its radius squared, so 6.05 into 10 to the power 6 whole square. This would come out to be 8.87 Newton per kg. Now we can take this in further. Now we can find the time period for this at Venus. It will be twice pi. The length is 9.81 by pi square. And the gravitational field strength at Mars is 8.8745. So the time period at Venus will be 2.10 seconds. Now in question 13, we are given that the particular line in a spectrum of light from the laboratory has a frequency of 6.13. So this is f naught, this is the laboratory value, 6.173 into 10 to the power 14. We are given that the same line of spectrum from a distant galaxy has a frequency of 6.142 into 10 to the power 14 hertz. We have to deduce what can be concluded about the distant galaxy. So f naught is 6.173 into 10 to the power 14 meter per second, and f is 6.142 into 10 to the power 14 hertz. Since the observed frequency is less than the original frequency, this is a redshift. So this is a redshift. Which means that the object is moving away from us. We can find the velocity. So the change in frequency by the original frequency will be equals to the velocity of recession divided by the speed of light. This will be 6.142 minus 6.173 into 10 to the power 14 divided by 6.173 to 10 to the power 14, which would be equals to v divided by 3 into 10 to the power 8. From this we'll get v equals to minus 1.51 into 10 to the power 6 meter per second. So we can draw a conclusion that the galaxy is moving away at a speed of 1.51 into 10 to the power 6 meter per second. Now in question 14, we are given that the tire of a racing bicycle contains nitrogen at a temperature of 22 degrees Celsius, and its volume is given, its pressure is also given. Now we are told that nitrogen is pumped into the tire, its volume remains constant, and the total mass of nitrogen including the added nitrogen is 2 grams. We have to calculate the increase in pressure assuming that the temperature remains constant. Now we are also given the mass of one nitrogen molecule over here. The pressure has changed, so this value has changed while the volume and the temperature has remained constant. We are also given its mass and the mass of one molecule. So we can find the number of molecules from here. The number of molecules will be the total mass, so 2.00 into 10 to the power minus 3 kgs, divided by the mass of one molecule. So this will give us the number of molecules over here. This is 4.283 into 10 to the power 22. Now we can use PV equals to NKT to find the final pressure after the nitrogen was added. So the new pressure is the number of molecules after the nitrogen was added, which is 4.283 into 10 to the power 22 times the Boltzmann constant, which is 1.38 into 10 to the power minus 23, and the temperature in Kelvin. The temperature remains constant, so it's 22 degrees Celsius or 22 plus 273 Kelvin, and we'll divide it with the volume. The volume is also constant at 2.85 into 10 to the power minus 4 meter cube. So the final pressure is 6.117 into 10 to the power 5 pascals. So the change in pressure will be equal to 6.117 into 10 to the power 5 minus 5.75 into 10 to the power 5 pascal. 5.75 into 10 to the power 5 pascal. We'll get a value of 3.67 into 10 to the power 4 pascal. Now in question 15, we are given that a teacher used liquid nitrogen to demonstrate low temperature physics, and the teacher dropped a peeled banana at room temperature into a flask of liquid nitrogen. We have to explain why the liquid nitrogen boiled when the banana was submerged in the liquid nitrogen. So the banana is at a higher temperature than the liquid nitrogen, so energy from the banana will be transferred, will be given to the liquid nitrogen, so it will be transferred away from the banana, which would contribute in the nitrogen molecules gaining molecular potential energy and boiling from liquid to gas. So energy is transferred. Now in question B, we are given that during the demonstration, the liquid nitrogen remained at its boiling point in a large flask, and that the teacher estimated that at least 0.5 kg of liquid nitrogen was needed to cool the banana from room temperature to the temperature of the liquid nitrogen. We are given the latent heat of vaporization of nitrogen, its boiling point in Kelvin, specific heat capacity of banana, the mass of the banana, and the room temperature in Kelvin. So the change in temperature of the banana, so mc del theta for banana, so m banana specific heat capacity of banana times the change in temperature of banana will be equal to this would be equal to the energy needed to vaporize nitrogen, or this would be the mass of nitrogen times its latent heat of vaporization. Mass of banana is 0.118 kg. The specific heat capacity for banana is 1.76 into 10 cube, and the change in temperature is 292 minus 77.4. The mass of nitrogen, we need to find the mass of nitrogen and check if this matches with the teacher's estimate of 0.5 kg. The latent heat of vaporization for nitrogen is 1.98 into 10 to the power 5. From this, if we calculate the mass of nitrogen required, if we calculate this value, we'll get a mass of, this will give us a mass of 0.225 kg. So this is much less than the teacher's estimate of 0.5 kg. So the teacher's estimate was inaccurate. Now on to question 16. We are given that Pluto is a dwarf planet which moves in an approximately circular path with the radius being approximately 5.91 into 10 to the power 12. So the mean radius is 5.91 into 10 to the power 12. The sun's radius is given. The surface temperature is also given. The intensity of radiation at Pluto will be the luminosity of the sun divided by 4 pi. I'll consider this the radius of Pluto's orbit, and this is the radius of sun. So this will be 4 pi rp square. Now we need to find the luminosity. To find the luminosity of sun, we'll use Stefan-Boltzmann formula. So luminosity would be equal to Stefan-Boltzmann constant 5.67 into 10 to the power minus 8 times the surface area of the sun, which would be 4 pi into radius of sun squared, so 6.96 into 10 to the power 8 squared, times its temperature in Kelvin raised to the power of 4. So if we calculate this, the luminosity of the sun would come out to be 3.906 to the power into 10 to the power 26 watts. So the intensity of sunlight at Pluto would be 3.906 into 10 to the power 26 divided by 4 pi times the radius of orbit of Pluto squared, so 5.91 into 10 to the power 12 squared. The intensity would come out to 0.890 watt per meter square. Now we need to find the time in years that Pluto takes to make one complete orbit around the Sun. Since this is a circular orbit, its centripetal force will be m omega square r, and this is provided by the gravitational force, which is gmm by r square. So 6.67 into 10 to the power g times the mass of Sun times the mass of Pluto divided by the orbital radius of Pluto squared. Here small this m is also the mass of Pluto. So from both sides the mass of Pluto can be cancelled out. The radius, if you send it over here, will become cubed. This is the orbital radius of P. So omega squared would be equals to g times mass of Sun by the orbital radius of Pluto cubed. Omega square is 2 pi by t. Now we can place our values over here. Mass of Sun is 1.99 into 10 to the power 30. The orbital radius is 5.91 into 10 to the power 12. So taking a root over on both sides, this will give us the time period, the orbital time in seconds. So if we have to convert this into years, we have to divide it with the number of seconds in 1 year, which is 3.15 into 10 to the power 7. So we'll get a value of 248.7. So basically 249 years. Now in question 17, we are given that Skylab was an early space station that orbited the Earth, which contained a body mass measurement device, this device was a chair connected to a stiff string. Now in question A, we are asked astronauts in orbit about this Earth are sometimes described as weightless, although they do experience a weight force. We have to explain why this may be described as weightless. Weightless is having no reaction force on you. The weight we feel is not our weight, but the reaction force. So if this was our weight, this would be our reaction force, the reaction force on us. This is the force we feel. If you were hanging on a rope, for instance, instead of the normal reaction, it would be the tension. The tension would be equal to the weight if you weren't accelerating. However, if you were in free fall, with no other forces on you, you wouldn't feel your weight. You would feel like you're floating. Now, if astronauts are in orbit, they are moving in circular motion around the Earth. So if it wants to move in a circular motion around the Earth, it needs to have a centripetal force towards the center. This centripetal force mv square by r is provided by its weight, by the astronaut's weight mg. So g becomes equal to v square by r. If g is equal to v square by r, there wouldn't be any contact forces on the astronaut like tension or normal reaction force. So they wouldn't feel any force, they wouldn't experience the contact forces. Now on to question 17b. We are given that the spring was tested without oscillating. A force of 175 Newton was applied to the spring and it deformed by 28.9 centimeters. When no one was sitting in the chair oscillated with a period of 0.858 seconds, and when one of the astronauts sat in the chair, it oscillated with a period of 2.26 seconds. We know that the time period is equals to twice pi root over m by k. Using the detail over here, the force and deformation, we can find the stiffness constant. So F equals to k del x. The force is 175 newtons. We have to find k, and the change is 28.9 centimeters, which is 0.289 meter. Or so k would be 605.5 Newton per meter. So the time period without the astronaut is 0.858 seconds. From this we can find the mass of the chair. If we square both sides, we can make aim the subject from beforehand to make our calculations easier. If we square both sides, we'll get t square on the left, 4 pi square into m by k on the right. Now if I want to make m the subject, I'll get t square divided by 4 pi squared k. So the mass of chair would be the time period before the astronaut sat on it, so 0.858 seconds squared, divided by 4 times pi squared times the stiffness constant 605.5. Oh, k would be at the top. It would be so the mass would be k times t squared divided by 4 pi squared. So mass of the chair, if we calculate it like this, we'll get 11.29 seconds. Mass of chair plus astronaut will be equal to the time period when the astronaut is on the chair times the stiffness constant 605.5 divided by 4 pi square, we'll get 78.34 seconds. Kg. And the mass of the astronaut will be the change in mass or the difference in mass between this. So mass of astronaut is 78.34 kg minus 11.29 kg. So the astronaut has a mass of 67.1 kg. Now on to question 18. We are told that Kruger 60 is a binary star system. The maximum wavelength, the peak wavelength, lambda max, is given, at which the intensity of radiation is around 850 nanometer. So the peak wavelength is 850 nanometer for Kruger A and 1500 nanometers for Kruger B. A website states that the surface temperature of Kruger A is double the surface temperature of Kruger B. We have to assess if this is accurate or not. So we have to use Wien's law for both. So for A, lambda max is 850 into 10 to the power minus 9 times temperature A equals to 2.898 into 10 to the power minus 3. So the surface temperature of Kruger A would be 3409 Kelvin. Now for B, the peak wavelength is 1500 into 10 to the power minus 9 times temperature of B So the surface temperature of Kruger B would be 1932 Kelvin. So the ratio of the surface temperature of Kruger A against Kruger B would be 3409 divided by 1932, which is 1.76. So the surface temperature of Kruger A is slightly less than double. So this is less than 2.00. So the surface temperature of Kruger A is less. You can also write slightly less because the difference is not that big. Now we are told that Kruger B can be used as a standard candle. In this question we have to describe how standard candles can be used to determine distance. So we just need a basic overview of how the standard candle method is used. We have to define what a standard candle is at first. So standard candles are basically objects in space that have a luminosity that we know. So stellar objects with known luminosities. Now we have to describe how we use standard candles and the standard candle method to find the distance to galaxies. So for that we have to find the standard candle in that distant galaxy and then measure the intensity of electromagnetic wave coming from that object, and then we can use the inverse square law of intensity equals to luminosity divided by 4 pi d square. So we can find the distance from here. We can label luminosity L and intensity I, so we can just put the equation. At last we'll show that how the equation is used. The intensity is luminosity divided by 4 pi d square. This distance, the distance of the standard candle from Earth is d over here. Now we can make d the subject. We'll get luminosity divided by 4 pi times intensity and the square root of it. Now in part C, we are given that NGC 1357, a spiral galaxy, is moving away at a speed of 2.02 into 10 to the power 6 meter per second, and that it is 8.7 into 10 to the power 23 meters away from the Earth. We have to calculate the value for the age of the universe in years. Now at the start, before the Big Bang, everything was at the same spot. So at t equals to 0, the distance between the Milky Way galaxy and NGC 1357 was 0 meters. Now after however many years the universe has been through, the distance between them has grown to 8.7 into 10 to the power 23. If we assume that it has been moving away from us at the same constant velocity since the beginning of the universe, we can find an estimate for the age of the universe. We know that since we are considering a constant velocity, we can use displacement equals to Vt. Now the displacement is 8.70 into 10 to the power 23 meters. The velocity is 2.02 into 10 to the power 6 meter per second, and t over here is the age of the universe. The age of the universe in seconds would be 8.70 into 10 to the power 23 divided by 2.02 into 10 to the power 6. Now to convert it into years, we'll divide this with 3.15 into 10 to the power 7. The value of t will get 1.2 0.37 into 10 to the power 10 years. So basically 13.7 billion years. Now we are given this question about binding energy. We have to explain why energy is released when a nucleus undergoes fission. So fission happens for something like uranium, and this causes its number of nucleons to decrease by forming smaller atoms, smaller nuclei. So it moves like this, so number of nucleons decrease. If the number of nucleons decrease, the binding energy per nucleon increases, and we'll write that down. If binding energy increases, energy is released. Or you can talk about it in terms of mass. If the binding energy increases, the total mass decreases, so the mass is converted into energy. This is enough for this question. We don't need to write further. Now in part B, we're told that nucleus of 238 uranium undergoes fission, and one of the fission products is tin. We have to estimate the energy released from the fission. Now uranium is over here. It has, this is its value, 14. Slightly more than that. For uranium, the binding energy per nucleon would be each 10 box is 2, so each small box is 0.2. This would be 7.8. Or if I go up from here, this would be 6.2, 6.4, 6.6, 6.8, 7, 7.2, 7.4, 7.6 is over here. So in the middle, it's 7.5 mega electron volt per nucleon. And this one would be 8.2, 8.4. So for tin, it's 8.4. We could also consider it to be 8.5 since this is quite in the middle. So if I draw it from here, it's in the middle. So this is 8.2, 8.4 and 8.6. In the middle, it's 8.5. So the increase in binding energy per nucleon would be increase in binding energy per nucleon it's 8.5 minus 7.5. So 1 mega electron volt And if we want the increase in energy if we want the total increase in binding energy, we have to multiply it with the number of nucleons, which is 238. So this would be 238 mega electron volts. Now we are given that we have to give the nuclear equation for the decay of strontium 90. It releases a beta minus particle, so this is 0, this is -1, and to balance it out we'll have 39 over here, so 39 minus 1 is 38, and the mass number would remain unaffected. Now in part 2 we are given that the activity due to strontium 90 is in one of the cans was measured 1.295 into 10 to the power 15 becquerel. We have to calculate the rate of energy release in watts due to the strontium 90 in the canister, given that energy released in each decay is 0.546 mega electron volts. So the power 1.295 into 10 to the power 15 is the number of decays per second. Becquerel is basically per second. So we have 1.295 into 10 to the power 15 decays per second. Each decay has an energy of 0.546 mega electron volt. So the power is 1.295 into 10 to the power 15 into 0.546 mega electron volt per second. But we want this in watts. So to convert this into watt, we have to convert the mega electron volt into joules. So this is 0.546 into 10 to the power 6 electron volt, and to convert electron volt into joule we have to multiply it with 1.6 into 10 to the power minus 19. From this we get a value of power to be 113 watts. Now the authorities claimed that the canister were 50 years old and that the activity of each canister when it was new was 3.7 into 10 to the power 15 becquerel. We have to assess the accuracy of the claim given that the half-life is 28.8 years. Now we know that the activity is the initial activity times e to the power minus the decay constant time that multiplied by the time. Now the decay constant would be ln 2 by the half-life. So if I want the decay constant in per years, we have ln 2 by 28.8. If we use that and find t, it should be 50 years old if the claim is correct. So the activity after 50 years is 1.295 into 10 to the power 15. So 1.295 into 10 to the power 15. This is equals to 3.700 into 10 to the power 15 times e to the power minus ln 2 by 28.8 t. We can move e to the power minus t ln 2 by 28.8 on one side and have 1.295 divided by 3.700 on the other. We can take a ln on both sides. We'll get minus t ln 2 by 28.8 equals to the natural log of 1295 by 3700. From here, if we calculate t is minus ln 1295 by 3700 times 28.8 divided by ln 2. From this we get a value of t. This would be 43.6 years. So this is not equals to 50 years. Hence the claim is inaccurate. If our value rounded up to 50, we'd say that it's close, so the claim is correct. So for example, if we got 48 years, it would round up to 50 in one significant figure. So we could consider that to be correct or accurate. But for 43.6, if we round it to 1 SF, it will be 40. So this is not correct. We have another question about radiation over here. We are told that unknown radioactive source was tested with a GM tube. The initial count rate is determined without an observer. And then we are told that when an aluminum sheet of thickness 0.5 cm was placed, the count rate decreased to background level. The teacher then removed the aluminum sheet and replaced it with a sheet of paper. There was no change in the initial count rate. We have to explain which type of radiation is emitted. Now, if it was alpha, if this was alpha emission, if alpha emission cannot go through a sheet of paper, so if this was alpha, the sheet of paper would stop it. Since we are told that there is no change in the initial count rate with the paper, it cannot be alpha because alpha would be stopped by paper and there would be a significant decrease in the count rate. Now if it was beta, it would go straight through the sheet of paper, so there would be no change, so it might be beta according to this information. Same for gamma. Gamma would go straight through paper, so it could be gamma or beta both from this detail. Now we have another detail over here, that when an aluminum sheet of thickness 0.5 cm is placed, the count rate decreases to background level. If this was beta, beta is stopped by aluminum, so it's logical that the count rate would decrease if this was beta because it cannot go through aluminum. However, if it was gamma, gamma can go through aluminum, so there shouldn't have been a significant decrease in count rate with 0.5 cm of aluminum for gamma, so this is not gamma. So from this information in this paragraph, we know that this is not alpha, and from this information we know that this is not gamma, so it must be beta. This is our description of why it can't be alpha. Now we also have to describe why it isn't gamma and it is beta. Now we have showed that this cannot be alpha and beta, and the last point would be identifying that it's beta. Now moving on to part B, we are told that the count rate R is recorded after gamma radiation has passed through a thickness of X. This is the count rate, equation of the count rate with respect to the thickness. R0 is the count rate without any absorbance, and mu depends on the energy of the gamma reflection. We are given a graph of ln R against X. To change this into a graph of ln R against X, we'll take ln on both sides. We'll get ln R equals to ln R0 plus ln e to the power minus mu x. We'll get ln R to be minus mu x plus ln R0. This is comparable to y equals to mx plus c. X is x, y is ln R, plus c is ln R0, and the gradient is minus mu. So the gradient of this graph will be equals to minus mu. So we can find mu from here. In the question we have to, if we look further into the question, we are also given how mu depends upon the gamma photon energy, and then we are given some gamma photon energy of different sources, and we have to find which source was used for the investigation. So from this graph we have to find mu. Then we have to check what energy it corresponds to. So for the value of mu we'll get a corresponding value of photon energy, and we'll see if that photon energy corresponds to 80, 122 or 360. So for this we'll consider this point and this point, this and this. Each 10 box on the y-axis is 100, so each small box is 10. So this value over here would be 510, 520, 530, 540. And this value over here would be 10, 20, 30, 40, 50, 60. So this value over here is 60. And the x values are 0 and 8. So we have 540 minus mu is the gradient, so 540 minus 60, and we have 0 minus 8. So mu would be minus 60, so 60 per centimeter. Now in this graph, if we apply that, we have the axis leveling on this graph is not the standard method, but the sizes of each small box varies, but each small box is the same unit apart. So between 1 and 10 we have 1 2 3 4 5 6 7 8 9. So 10, from 1 to 10 we have 9 boxes. So this is 1 2 3 4 5 6 7 8 9 10. So each small box is 1 over here. Now in this case each small box would be 10. This is a sort of logarithmic scale, but without putting a ln over here. So from 10 to 100 each small box will be 10 units. From 100 to 1000 each small box will be 100 units. So this is 20, this is 30, 40, 50, 60, 70. So since we have already got our value of 60, we don't have to look further. So the corresponding value for 60 is our answer. The x-axis is a normal axis, while the y-axis is sort of a logarithmic one. Now in the x-axis we have 1 2 3 4 5 6 7 8 9 10. So 10 boxes represent 100 units. So 100 by 10, each small box is 10 units. So this would be 10 20 30 40 50 60 70. So the energy of the gamma photon equals to 70 kilo electron volt this is closest to xenon, which has a photon energy of 80. Instead of doing the calculation for the gradient over here, you'll do it over here. You'll show the gradient calculation over here. It's better to show and draw a triangle on the graph like this. So draw a triangle like this over here. Show the points you have used to calculate the gradient, and then show show a working like this on the graph. So you'll have 1 2 20 30 40 50 60. Show that the corresponding energy for mu equals to 60 per centimeter is 70, and then you write the conclusion that photon energy is 70 mega electron volt, which is closest to, it's kilo electron volt, not mega. 70 kilo electron volt, which is closest to 80 kilo electron volt. So the source is 133 xenon. Now moving on to the last question of this paper. We have our 6 marker over here. For the 6 marker, we are told that in the core of a main sequence star, nuclear fusion is converting hydrogen into helium. We have to explain the conditions required to bring about and maintain fusion in a main sequence star. So we have to state the conditions for fusion, and we have to write down why the conditions are what they are, and after that we have to describe how it happens. So the most important criterion would be the high temperature in the core and the high pressure in the core, and we have to separately explain why each of these conditions are required. So let's write about the temperature first. I accidentally mentioned pressure. It would be due to density, not pressure. So we need a high temperature and high density. We need the high temperature because we want the nuclei to have high enough kinetic energy to fuse, because it has to overcome the electrostatic repulsion, and it must have a high density so that the nuclei are closely packed together, so they collide more often and have a high collision rate. This is the part about the high temperature stuff. Now we have to talk about the high density. High collision rate means the number of collisions happening between the nuclei per unit time. So if we have a high density, there will be a lot of stuff packed together. So if we picture something very dense over here, so if there are nuclei like packed like this over here, there's a high chance they'd collide with someone. However, if they're loosely packed like this, they might go on like this and not collide with anything at all. But in this case, on the left, the chances of collision will be much higher, so the rate of collisions will also be high. And if a high rate of collision is maintained, fusion will be maintained. And that's it for 21A. Now moving to 21B, we are given that helium nucleus is a stable nucleus of 2 protons and 2 neutrons. We have to calculate the binding energy per nucleon of a helium nucleus. We are given the mass of a proton, the mass of a neutron, and the helium's mass. The binding energy is change in c square, speed of causality squared, or the speed of light in vacuum squared, times the change in mass. The change in mass over here would be 938.28 into 2 plus 939.57 into 2 minus 3727.6. Since we are given the mass in MeV per c square, we don't have to use the energy equation. We directly can find the energy in mega electron volts. The total binding energy in mega electron volt would be, if we calculate this, we'll get 28.1 mega electron volt per c square. The change in mass is equal to the change in energy, or the binding energy. This is the total binding energy. Since they want this in joules, we have to find the binding energy in joules. So 28.1 into 10 cube electron volts, and multiply it with 1.6 into 10 to the power minus 19 to convert it into joules. So this would be 4.496 into 10 to the power minus 15 joules. This is the total binding energy. So the binding energy per nucleon would be the total binding energy divided by the number of nucleons, which is 4 in this case. So binding energy per nucleon is 4.496 into 10 to the power minus 15 by 4. This is equal to 1.124 into 10 to the power minus 15 joules. Now in the last part, we are asked that the binding energy per nucleon of helium is relatively large. We have to explain why this makes the helium nucleus stable. If the binding energy per nucleon is high, this would mean that a large energy is required to break the helium nucleus apart, since the binding energy per nucleon is the energy required to remove a nucleon. So if the energy required to remove a nucleon is large, a large energy is needed to break the nucleus. And that's it for this paper.